First problem. We want to argue that the following statement is true in general. If every millionaire is happy or not busy, then every busy millionaire is happy. Solution. Let's take a busy millionaire and call it X. We know by assumption that X is happy or not busy, but we assumed X is busy. So X must be happy. This simple informal inference is of the kind that is very typical to predicate logic, as we shall see when we define natural deduction in predicate logic in a moment. Next problem. Use unary structures to show that the following statement is not true in general. If every rainy day in August is windy, then some windy day in August is rainy. Solution. Let M be a non-empty set of hypothetical August days, P0 the set of rainy days in M, and P1 the set of windy days in M. The statement then says, quote, if P0 is contained in P1, then some element of P1 is in P0, unquote. It is clear that in such generality this cannot be true. For example, if P0 is empty, then P0 is contained in P1, but no element of P1 is in P0 because P0 is empty. Next problem. Use unary structures to argue that the following statement is not true in general. If there are millionaires and every millionaire is happy or not busy, then no busy millionaire is happy. Solution. Let M be a non-empty set of hypothetical millionaires. P0 the set of happy millionaires in M, and P1 the set of busy millionaires in M. The statement then says, quote, if every element of M is in P0 or in the complement of P1, then no element of P1 is in P0, unquote. In such generality this cannot be true. For example, if M is a singleton set containing just one element, one person, Tom, P0 is M and P1 is also M. Then every element of M is in P0 or in the complement of P1. But some element of P1 is in P0. Next problem. Draw a unary structure where two predicates divide the domain into three parts. Give an everyday life example. Solution. We let M be, for example, the set of all fins, A0 the set of fins that are taller than 190 centimeters, and A1 the set of fins that are shorter than 170 centimeters. Next problem. Draw a unary structure where three predicates divide the domain into 6 parts. Give an everyday life example. Let M be, for example, the set of all Europeans, A0 the set of Europeans who live in Finland, A1 the set of Europeans who speak French, and A2 the set of Europeans who live in Italy. Next problem. Is it true that if a tile model has left of every blue tile a red tile, then it has right of every red tile a blue tile. Let's consider 3 tile models. In the first, it is indeed true that left of every blue tile is a red tile and right of every red tile is a blue tile. However, in the second tile model, again left of every blue tile is a red tile, but right of the last red tile there are no blue or other tiles. The third tile model is interesting. Left of each of the 0 blue tiles is a red tile, but it is certainly not true that right of every red tile there is a blue tile. So the answer to the question is no. Next problem. Is it true that if a tile model has left of every blue or yellow tile a red tile, and the model has a red tile, then it has a yellow tile? Let's consider the following 2 tile models. In the first tile model, it is true that left of every blue or yellow tile there is a red tile, and there is a red tile in the model, but there is also a yellow tile. However, in the second model, left of every blue or yellow tile there is a red tile and there is a red tile in the model, but there are no yellow tiles. So the answer to the question is no. Next problem. Suppose a graph has 10 edges. How many vertices must it at least have? What if the graph has 100 edges? Solution. Every edge is connected to 2 vertices, namely the 2 endpoints of the edge. From n vertices one gets thus at most n times n minus 1 over 2 edges. For n less than 5 we get less than 7 edges. For n equals 5 it is possible to get 10 edges as the below graph shows. For 100 edges we need 15 vertices. Argue that if a graph has at least 2 vertices and some vertex has every other vertex as a neighbor, then every vertex has a neighbor. Solution. Suppose x is a vertex which has every other vertex as its neighbor. Suppose then y is an arbitrary vertex. If y is not x, then x is a neighbor of y, so y has a neighbor. If y equals x, we argue as follows. Since the graph has at least 2 vertices, there is a vertex z different from x. By our choice of x, z is a neighbor of x. But x equals y in this case, so again y has a neighbor. Show that the following statement is not true in general in graphs. If some vertex has every other vertex as a neighbor, then every vertex is a neighbor to a vertex that has every other vertex as a neighbor. Solution. We consider the graph of the picture. In the graph of the picture, the middle vertex has every other vertex as its neighbor, but its neighbors are the 3 extreme vertices, and they do not have the property that every other vertex is their neighbor. So this is the desired counterexample. Show that the following statement is not true in general in graphs. If every vertex has a neighbor, then some vertex has every other vertex as a neighbor. Solution. In the graph of the picture, every vertex has a neighbor, but no vertex has every other vertex as its neighbor. So this is the desired counterexample. Suppose a graph has 6 vertices. Show that there are 3 vertices that are all neighbors of each other or all non-neighbors of each other. Solution. Take one vertex, call it V. It can be just any of the vertices. Whatever V is, the remaining vertices are divided into a set A of neighbors of V and a set B of non-neighbors of V. Since A and B together have 5 elements, one of them must have at least 3 elements. Suppose it is A. If the elements of A are not neighbors of each other, we are done. So let us assume 2 elements of A are neighbors. Let us call them U and W. Now U, V and W are all neighbors. We have to consider also the case that it is B, which has at least 3 elements. We proceed in the same way. If all the elements of B are neighbors, then we are done. Otherwise there are U and W in B that are non-neighbors. Now U, V and W form a triple of elements that are all non-neighbors of each other.